All right, let's just jump right in. If you've ever stared at a chemistry textbook and felt totally overwhelmed by the sheer volume of equations, the unit conversions, and those really abstract concepts, well, you are in exactly the right place. Today, we're going to completely demystify the intimidating math of basic chemistry. We're going to break down exactly how chemistry moves from qualitative observations of the world around us to the precise quantitative math that makes modern science actually work. So, to kick things off, what do ancient Harappan metalworkers and modern smartphone batteries actually have in common? The answer is transformation. Chemistry, at its core, is the fundamental science of transformation. It's the study of material substances, their structure, their properties, and how they react and change. And, it's not just something that happens in modern laboratories with people wearing white coats and safety goggles. It's a practice that has literally driven human progress for millennia. In fact, long before the scientific revolution, ancient India made massive contributions to this science of transformation. We have archaeological evidence from Harappa and Mohenjo-daro that shows this incredible deep knowledge of pottery, glass, and metalworking. Ancient traditions like Rasavidya covered metallurgy and medicine. And incredibly, Acharya Kanda actually proposed the concept of very small, indivisible particles called paramanu way before modern atomic theory was formalized. So our ancestors were already mastering the fundamental science of matter centuries ago. Here is our roadmap for this explainer. 1. Matter and its origins. 2. The language of measurement. 3. Laws of chemical combination. 4. The mighty mole concept. 5. Decoding chemical formulas. And 6. Stoichiometry and chemical reactions. Let's get to it. Section 1. Matter and its origins. Defining the basics. The definition of matter is brilliantly simple. It is basically anything that has mass and occupies space. So your coffee cup, the air you're breathing right now, the device you're watching this on, it's all matter. And depending on how its particles are arranged, it primarily exists in 3 interconvertible physical states. We're talking solid, liquid, or gas. And the cool part? You can change these states just by tweaking the temperature and pressure. Now, beyond its physical state, we classify matter into pure substances and mixtures. This is a really high-value exam reminder, so definitely lock this in. A homogeneous mixture, like a thoroughly mixed sugar solution, has uniformly distributed components. You can't actually see the different parts. A heterogeneous mixture, on the other hand, like dirt mixed with greens, has a non-uniform composition, where the different components are clearly visible to the naked eye. Just keep that uniform versus non-uniform distinction sharp in your mind. Section 2. The language of measurement, setting the ground rules. Okay, there are 7 fundamental base units of the International System of Units, or SI. Literally everything else we measure in chemistry is derived from these. We have length, mass, time, current, temperature, amount of substance, and the luminous intensity. And here is a crucial pro tip for you. Do not confuse mass and weight. Mass is the constant amount of matter in a substance. Weight is just the gravitational force acting on it. Your mass is exactly the same on Earth as it is on the moon, but your weight would be drastically different. So the crucial point in all this is making sure our measurements are actually good. And that brings us to another vital distinction: accuracy versus precision. Accuracy is how close your measured value is to the true actual value. Basically, did you hit the bullseye? Precision, on the other hand, is how close your repeated measurements are to one another. Are all your darts grouped tightly together, even if they completely miss the center? Measurements can be highly precise but totally inaccurate, or accurate on average but wildly imprecise. In science, you really need to strive for both. When we calculate these measurements, we use something called dimensional analysis. This is how we convert from one unit to another by setting up fractions where the unwanted units perfectly cancel out. Now, why does this matter so much? Because correct unit cancellation acts as a built-in logic check. If your units don't cancel out correctly to leave you with the unit you actually want, you instantly know your math is set up wrong. It is an absolute lifesaver on exams. Section 3. Laws of chemical combination, building the bridge. Chemistry is governed by strict quantitative laws, like the law of conservation of mass, which tells us that matter cannot be created or destroyed. These historical laws were huge because they supported Dalton's atomic theory, which treated atoms as the fundamental building blocks of matter. Think of these early rules as a bridge. They connect the observable mass relationships, the macroscopic stuff we can easily weigh on a scale, directly to the invisible microscopic world of atoms and molecules that we just can't see. Section 4. The mighty mole concept, the climax. Take a second and just try to process this massive number, 6.022 times 10 to the 23rd power. This is Avogadro's number. It is an almost incomprehensible, mind-boggling scale. To put it in perspective, if you had a mole of marbles, they would cover the entire surface of the Earth several miles deep. But because atoms are so unbelievably tiny, a mole of water molecules fits easily inside a standard drinking glass. Mathematically speaking, 1 mole of any substance contains exactly Avogadro's number of specified elementary entities, whether we're talking about atoms of hydrogen, molecules of water, or ions of salt. The mole is simply chemistry's ultimate counting unit. Just like the word dozen always means 12, the word mole always means 6.022 times 10 to the 23rd. In practice, we use these essential relationships all the time. You can find the number of moles by taking your given mass and dividing it by the molar mass from the periodic table. And from there, you can find the exact number of particles by multiplying those moles by Avogadro's number. The mole acts as the universal translator between the physical weight of a substance sitting in your hand and the exact number of microscopic particles it actually contains.
Section 5. Decoding chemical formulas, putting it into practice.
So, if you're ever given the percentage composition of an unknown compound, just follow this simple 5-step workflow. Step 1. Assume you have a 100-gram sample that instantly turns those percentages right into grams. Step 2. Divide those grams by the atomic mass to get moles. Step 3. Divide all those mole values by the smallest one you found to get a simple ratio. Step 4. Multiply if necessary to make sure they are crisp, clean, whole numbers. And Step 5. Write out your empirical formula, which is just the simplest whole number ratio of the atoms. Now, once you have that empirical formula, you aren't quite finished. You might need the true molecular formula, which is the actual number of atoms in a single molecule. You can always find the mass percentage of an element to double-check your work, but to get that molecular formula, you have to calculate a multiplier, which we call N. You just take the true molecular molar mass and divide it by your empirical formula mass. Multiply your simple empirical subscripts by that N, and boom, you have the exact molecular formula. Section 6. Stoichiometry and chemical reactions, the final calculation. Look, stoichiometry can look absolutely terrifying at first glance, but here is the ultimate golden pro tip. Always convert your given quantity into moles first. Never ever try to compare grams of one substance directly to grams of another. It won't work. Convert to moles, use the coefficients from your perfectly balanced equation to find the ratio, and then convert back to whatever unit the question is actually asking for. But what happens when things aren't perfectly portioned out in the real world? Well, that's where the limiting reagent dictates the final outcome. Think of it like baking a cake. If your recipe calls for 2 eggs and 2 cups of flour, and you have 100 cups of flour in the pantry, but only 2 eggs, you can still only bake 1 cake. The eggs completely limit the reaction. In chemistry, once the limiting reagent is exhausted, the reaction stops entirely, no matter how much extra stuff you have just sitting around. All right, let's rapidly synthesize what we've covered today. This entire subject is really about how chemistry moves from qualitative observation to precise quantitative description. Chemistry is ultimately the universal language of conversion. We are constantly converting between units, between physical mass and invisible moles, between chemical composition and formulas, and between starting reactants and final products. And that leaves us with this final provocative thought to ponder. If just one single mole of a substance holds over 600 billion trillion atoms interacting with each other, try to imagine the sheer scale of the chemical universe. How many brilliant, completely undiscovered chemical combinations are out there, just waiting to be mathematically decoded, understood, and converted into the materials, medicines, and technologies of our future? Thank you so much for exploring this amazing topic with me. Keep learning, keep questioning, and I'll see you in the next explainer.